Acid-base chemistry is a very important part of organic chemistry, and though we have covered it in some detail already in the lecture, I would like to go back and review just a few concepts that we did discuss this semester, and then also some concepts from your general chemistry 2 study of acids and bases to kind of remind you of some of the structural elements that are associated with predicting acidity and basicity. First of all, I'd like to take a look at this abbreviated pKa table. As you notice here, these are some pretty common compounds that we study in organic chemistry. And the pKa for HCl, of course, is very low because HCl is a strong acid. Here is acetic acid, which is up very close to 5. Water and ethanol, both up around 16. The alkyne around 25. And of course, these things are not very acidic at all. But these are important species to consider because the more acidic a species, the less basic its conjugate base, and vice versa. The less acidic a given species, the more basic its conjugate base. So what that means is that things over here on the chart are quite basic, whereas things over here, though we don't have too many strong acids here shown, tend to be much more acidic. Anything up here on the chart could protonate any conjugate base over here, and any conjugate base over here could deprotonate any of the acids up here. So basically, water could protonate anything, well, these two are about the same, but anything lower than it on the base side of the chart. And then the amidion could be protonated by anything higher than ammonia on the acid side of the chart. Now, we spent a lot of time looking at predicting the outcome of acid-base reactions, and this is a very important process for you to be able to go through because we're going to look at a lot of mechanisms over the course of the semester where an acid-base reaction is critical to one or more of the steps in the mechanism. And so here you see an alkyne with pKa of around 25 being mixed with an amide ion, and that amide ion is capable of completely deprotonating the alkyne, and that's because if you look at the the ammonia, which is the conjugate acid of that amide ion, its pKa is 38, so it's the much weaker acid. The stronger acid is always going to push the reaction in the opposite direction. And then if you wanted to consider the K for this reaction, we of course can just use this equation here. But often, if you just look at what is the stronger acid, whether it's the item that would be on the left side or the right side of the reaction, you can predict, okay, this one, much stronger acid, it's going to push the reaction in that direction. This one is the weaker acid, so it can't push it in the opposite direction. So acid-base chemistry is really important in our study of organic chemistry also because of its effect on the solubility of various materials. This will be particularly important to you in the lab, but it will also be important as we discuss the appropriate solvents to use in various chemical reactions. And so here you can see benzoic acid, which is an insoluble compound in water. Now, you can dissolve just a little bit of it, but it's such a small amount that it's almost negligible. However, if you deprotonate it using, say, a base like sodium hydroxide, now you have the benzoate ion with sodium as its counter ion, and this is much more soluble in water. And so this is a very useful way to separate various compounds in an acid or in a reaction mixture based on their acid-base properties. And so if you were to look at the aniline compound down here, that's a benzene ring attached to an NH2 group, the amine group, well, this compound is water insoluble, but the amine group can become protonated by an acid like HCl, and then it becomes a water soluble salt as the amine hydrochloride. And so this is actually something you'll often see in pharmaceuticals, is some sort of amine hydrochloride as a means to make the compound soluble in water so that your body can take it up in the digestive tract. One other thing that I should mention here is, as you look at this structure here, this is showing you that when you have HCl, the H plus really isn't specifically associated with the chloride ion. It actually has protonated water. And so what that means is that hydrochloric acid, because it's such a strong acid, when you put it in water or you put it in ethanol, what it will do is it will just completely protonate the solvent, and that will actually then act as the acid. Here's another example of how solubility can be really important. This, in a biological sense, aspirin, or acetylsalicylic acid, is of course an analgesic, a pain reliever, antipyretic, brings down your fevers, anti-inflammatory, reduces the inflammatory response. In its neutral form, the aspirin is not very soluble in water, but it is soluble enough to pass, or it is soluble in the membrane of cells, and can then be transported into the cell where it's needed for its effects on various chemical reactions to take these actions in the body. In its ionic form, though, when it becomes deprotonated, it can be taken up by it's soluble in water and can then be taken up by the bloodstream to be transported to those cells. So as I mentioned a couple slides ago, when you put HCl in water, what happens is it completely ionizes. So let's take a look at that. If I take HCl plus H2O, the reaction essentially goes 100% to H3O plus Cl minus. Now, if we were to dissolve a strong acid in something like ethanol, a very similar process will take place. Let's say that we had this time HBr plus, we'll say ETOH for ethanol. This will also react 100% to give us the protonated ethanol molecule plus a bromide ion. Now, in this case, the pKa here is about, I'm just guessing, I don't have the pKa chart right in front of me, but it's going to be around -9. And it turns out this acid is around -2 or 3. And so if we look at this, this has a K value of around 10 to the 7th, or 10 million. So this reaction lies far to the right. And so here again, we're looking at the protonated form of ethanol, whereas over here we're looking at HBr as the acid. This is actually acting as the base, not as an acid. So we're not looking at a pKa of 16. Well, this is what we call a leveling effect of a solvent, because even though HBr has a pKa of around -9, its effective pKa is going to be around -2 to -3 in ethanol, because that's the acidity of the protonated ethanol molecule. Whereas if we look at this up here, water is, or the hydronium ion is going to be our strongest acid again, probably around pKa of -2. In the case of bases, if we were to take an amine like, an amide ion like ethyl amide, which has 2 lone pairs, a hydrogen, an ethyl group, and then a formal negative charge. If we were to put this in, say, something like isopropyl alcohol as a solvent, this amide would just completely deprotonate the isopropyl alcohol. So let me show that real quick. Grabs that hydrogen, pushes those electrons back onto the oxygen, and now we have our amine which has one more proton than the amide ion did over there. And then we have the isopropyl alkoxide ion. And now, if we compare our pKa's, of course, this is acting as the base, so we'd have to think of this as the acid. Alcohols are all typically around 16. This one might be just a little bit higher because of the degree of substitution, but we'll just estimate it around 16. This one's around 38, so whether we estimated that one as 16, 17, 18, it wouldn't really matter because this is so much less acidic. And so as a result, this reaction lies far to the right, so once again 100% to the right. So what that means is that if you want a really strong base like the amide ion for deprotonating some species, for instance, if we wanted to deprotonate say a terminal alkyne where we had a triple bond and a hydrogen, this has a pKa of about 25. And so if this has a pKa of about 25, well, the amide ion, the conjugate base of this amine would certainly be strong enough to deprotonate it. But if this was in a solution of isopropyl alcohol, the isopropyl alcohol would be present in huge excess. Additionally, it would be a much stronger acid than the alkyne down here. And so this is the one that would become completely deprotonated, and none of this would react at all. And so that's the acid-base leveling effect of solvents, that you can't have an acid stronger than the protonated version of a solvent, and you can't have a base stronger than the deprotonated version of the solvent.